In the last lesson, we learned how we could visualize vectors geometrically, and when we draw them, how we could actually find those scalar quantities that define their magnitude, and how we can use the angles between them in order to solve application problems. What we want to take a look at now is how we can visualize and work with vectors more algebraically, as opposed to having to draw them in order to find out what their resultant might be. We can visualize vectors drawn on the x and y coordinate plane by starting every vector with an initial point at the point 0, 0, and terminal point at some point in the plane. So if this is, let's say, the x coordinate, and this is the y coordinate of that vector, then I could see that the terminal point will end at the point xy. And the way that we define this vector now is simply by calling vector u, algebraically, the vector that began at 0, 0, ending at xy. We simply write it as the ordered pair xy, but we now use these angle brackets in order to define that vector. We refer to this as component form of the vector. So if you ever see that a vector is in the form x comma y, that simply means that it's describing the terminal point of that vector u. Now that we've defined this since we've defined this vector in this given way, we could also come up with a formula for finding the magnitude of that vector. Now keep in mind the magnitude is nothing more than just the length of this vector, which you might notice is the hypotenuse of that right triangle. So I'm simply going to take x squared plus y squared and take the square root. And so the magnitude of a vector is found by simply using the Pythagorean theorem. Now we could take it a step further as well and recognize that if we are given an angle of that vector, sometimes referred to as the direction angle, okay, then that direction angle can be found again by using trigonometry, recognizing that if we're given the x and the y coordinates, what we're really given is the opposite and the adjacent side. So I should be able to see as well that the direction angle can be found by saying tangent theta is equal to y over x. So now we've seen that simply by using the terminal point of that vector, which is really nothing more than just the x and y coordinates of the terminal point, we can find the angle at which the vector is located and also the magnitude or the length of that particular vector. Now, just to describe this angle in a little bit more detail, we need to make sure that the angle or the direction angle is always going to be somewhere in the interval from 0 to 360 degrees, so that we're always thinking about it as going counterclockwise starting at the x-axis. So when we have component form of this vector, that's pretty helpful if we know the x and y coordinates, but a lot of times we don't know the x and y coordinates. Instead, oftentimes all we know is how long the vector is and what the direction angle is. So let's look at a couple of other relationships on this triangle. So let's recognize first that sine of theta, well, let's start with cosine theta. So cosine of theta is equal to the x component over the hypotenuse. But notice the hypotenuse is the magnitude of u. Notice that we can't just call it u, because that would imply that u is a vector when really what we're dividing by is the length of that vector. We could also see that sine of theta is equal to the y coordinate over the magnitude of u. So if we just multiply both sides by that magnitude of u, that shows me that x is equal to the magnitude of u times cosine theta. And the y coordinate is equal to the magnitude of u times sine of theta. So now, other than component form, which uses the x and y coordinate to give the vector, now we can look at it differently. We could also see that vector u is equal to the x coordinate, which is the magnitude of u times cosine theta, and the y coordinate, which is now the magnitude of u sine theta. So this form is now referred to in trigonometric form. So the advantage of trigonometric form is that oftentimes in some scenarios, all we're given is the magnitude of the vector and the angle at which it turns. So we're just told that the angle is, say, 30 degrees and the magnitude is 5. And so now I want to use that information to find the vector u, and now I've got two different forms with which to use. I can simply use the component form, or I can use trigonometric form. Now in this example, we want to find vector u, and we're given the information that the magnitude of vector u is equal to 16. And we're told that our angle, our direction angle, is 120 degrees. So we want to find vector u, which we know has the form of the magnitude of u, rather in our angle brackets because it's a vector, the magnitude of u times cosine theta, and the magnitude of u times sine theta. Now it makes sense that obviously the x coordinate is cosine theta and the y coordinate is sine theta because that's what we derived from our unit circle. But that was simply because we were on the one unit circle where the hypotenuse was 1. So if the hypotenuse is anything else, like the magnitude of u, then all we're going to have to do is multiply cosine theta and sine theta by that hypotenuse, or that magnitude, in order to find our quantity. So this gives us that the magnitude of u is going to be equal to 16 times cosine of 120 degrees, and the y-coordinate is 16 times sine of 120 degrees. So even though we didn't know the horizontal component or the vertical component of our vector, what we can do is use the unit circle here in order to find out what my cosine and sine of 120 are. Okay, so cosine of 120 degrees is negative 1/2. And now we see that sine of 120 degrees is positive root 3 over 2. And therefore, we know what our horizontal and vertical components are. We see that vector u is going to be negative 8 and 8 root 3. And so we've turned from trigonometric form into component form. So I'd now like to remind us about what we did before when we graphed the sum of two vectors analytically or graphically. So let's just say that I have this is vector u and this is vector v. And I'd like to find u plus v. Well, graphically, I applied the parallelogram law. And that was where I just took the vector v and put it onto the tail end of u. And I needed to make sure that it was drawn with the same magnitude. Okay. Or if I wanted to draw it u at the end of v, I could do that as well. And see that this approximately, if these were drawn parallel to each other, should be approximately what that value is. Now, notice that this x coordinate is a and this y coordinate is b. And if we look at the vector v, we could see that this x coordinate is c and this vector coordinate, or this y coordinate is d. But now what I want to do is find out what this point is up here where they end. And so if I want to find that x coordinate right here, I should realize that what I've done is I've just added this extra amount onto c, and this extra amount onto d. So if this extra amount is a, and this extra amount is b, then notice that all I have for my vector u plus v is that I'm adding together c plus the additional a. And what I could see for my y-coordinate is that I'm taking my value d and adding on the additional amount of b, which is essentially going to end at this location here. Okay, so that would mean that I have this d plus this extra amount of b. So hopefully what you can recognize geometrically is that by using the parallelogram law, all we're doing algebraically is adding the x coordinates, which is a plus c, and adding the y coordinates, which is b plus d. So taking the sum of two vectors is done in this way. Now I'd like to take a look at how we can think about u minus v, both geometrically and algebraically. So let's say that I had these two vectors, u and v, and now I wanted to find the difference between the two vectors. So the first thing I'd like you to recognize is that u minus v means the same thing as taking u and adding the negative of v. So if I want to add the negative of b, then I need to flip this vector around in order to be going in the exact opposite direction, which would take me to right here. So this would be negative v. So if we now look at where our coordinates are here, then let's recognize that this is our c value, this is our d value, and this x coordinate is a, and this y coordinate is b. So if I now wanted to add these vectors together, notice that I can now add u plus negative v, which means that this is what I'm going to be adding on. And what my goal is now is to find what that resultant vector is going to be, which ends right here. And that would be my vector u minus v. So let's again look at how we could find what that terminal point is for u minus v. So we should recognize first that this point at the end of negative v is just negative c and negative d. So notice in order to add u minus v, or I'm sorry, in order to subtract u minus v, what we really needed to do was just add negative v onto the end of u. And notice if I now add the x and y components, what I'm doing is adding a plus negative c, or rather a minus c, and I'm adding b plus negative d, or in other words, b minus d. And so now you can see that in order to add two vectors together, I simply add the corresponding components, and in order to subtract two vectors, I simply subtract the corresponding components. Now I'd like to take a look at one last scenario where we take a vector u and we multiply it by some scalar that we'll call k. Well, in other words, that would mean that I'm taking k and I'm multiplying by the vector a, b. We just want to see what we're able to do algebraically here. So let's say that you have this vector u, which is ab, and now I want to multiply it by a number. Let's say 3 or 2 or negative 4. We want to see geometrically what does that do, and analytically what happens as well. So for this particular vector, what I've done is I've actually just doubled the vector. So let's think of this new vector as being 2 times vector u. Okay. Well, if that was 2 times vector u, then that would mean that this distance here would simply be another distance of a, and this distance to the y coordinate, which would be right here, would be another distance of b. So in other words, the x and y coordinates would be 2b and 2a. So it looks like when I multiplied the vector by 2, all that happened is that I multiplied each component by 2, and therefore a scalar multiple of a vector is nothing more than just a scalar multiple of each component. So now we can not only geometrically see what's going on when we add some vectors, subtract vectors, and multiply by a scalar, but that analytically or algebraically, it's really quite simple because all we're doing is either adding the x and y components, subtracting the x and y components, or multiplying the x and y components by a particular scalar. Let's put all of this together with an example. So let's start off by looking at these two vectors, u and v, and we'd like to graph those on a coordinate plane. We should see that vector u has a terminal point at -2, 1. So that means that the terminal point is going to end at -2, 1, while for the vector v, the terminal point is at 4, -3. So that terminal point will end at 4, -3. And so now we just need the vectors connecting to those points. Well, in order to add 3u plus 2v, we first of all have to think about what is 3u going to be, and separately what is 2v. So these are just scalar multiples of the indicated vector, and so we're simply multiplying 3 times the vector -2, 1, and we're multiplying 2 times the vector 4, -3. Now remember, all we're doing with scalar multiples is multiplying each component. And so this gives us, for 3u, the vector -6, 3. And for vector 2v, we know that that's going to be the vector 8, -6. So if we graph each of those, then notice that 8, -6 is, or rather -6, 3 is going to be at the x coordinate of -6 and the y coordinate of 3. And so notice that that's going to be at this point here. But notice that that's just going to be 3. There's another vector u and another vector u, which means that that entire length is going to be 3u. And likewise, if you go to the other side, we see that the vector 8, -6 is going to have an x coordinate of 8 and a y coordinate of -6, which means that it's going to be right about here, which you should notice is exactly twice as long as vector v. So now that we've tripled vector u and doubled vector v, we can now add the two together. So notice by adding the two, we know that taking 3u and adding 2v means that all we need to do is add together the original vectors that we got up top, which were -6, 3, and 8, -6. And when we add those two results together, we get our final result of 2, -3. So 2, -3 is the vector 3u plus 2v. So that's how we were able to do it analytically or algebraically. But after doing this geometrically by doubling v and tripling u, keep in mind that in order to add 3u plus 2v, we just need to tack on one vector to the tail end of the other. Now, if we've done it right, we should end at the point 2, 2, and -3. So let's take a look at how this would happen. So if we start by drawing 3u, which is right here, and we add 2v, then that means we're going to start at the terminal point of 3u. And we're going to move 8 units horizontally and -6 units vertically, which means by taking 8 units horizontally and -6 units vertically, then notice what we're doing here is we're just adding on 2v to the end of u. So add 2v onto the end of u, and notice that the vector that's left is the vector right here. So the triangle that's formed is this triangle over here. That's the vector of 3u, 2v, and the sum of the vectors 3u and 2v. Okay. Now, one important aspect of physics a lot of times is being able to find a unit vector. Now, a vector, or a unit vector, is simply a vector with a magnitude of 1. And there's 2 very special unit vectors. One of these unit vectors is the horizontal unit vector. That's 1 unit long. And the other unit vector that's important is the vertical unit vector. That's also 1 unit long. And so these are given special names. So the vector in the horizontal direction is referred to as vector I, and the vertical unit vector is referred to as vector J. So we should see the vector I is equal to the vector 1, 0. And we can see that J is the vector 0, 1. So any vector that happens to be 1 unit long is considered a unit vector, but these are 2 very special vectors. So I'd like to take a look at the vector 3, 2 that's going to end at the terminal point of 3, 2. Let's say that that vector is considered vector u. Now I know that this vector that ends at 3, 2 is considered the vector u equals component form of 3, 2 in angle brackets. But I'd like to look at this a little differently, because that would imply that this distance horizontally is 3, and this distance vertically is 2. But if we take a look at this in a little more detail, look at the fact that I is horizontal by 1 unit. So what if I were to add a second I and a third I? Then notice that distance right there is referred to as 3i, 3 of those horizontal unit vectors. And what if I were to draw J? Well, drawing J once would end here. Drawing J a second time would end at the terminal point of vector u. So that would simply be 2j. Now, by thinking about the way that I have added vectors together, then all I've done is I've taken 1i plus another I plus another I plus 1j plus another j. And so in other words, what we've really done here is we've taken 3i plus 2j, which is why u in a different form could be thought of as taking 3 of the horizontal unit vectors and adding 2 of the vertical unit vectors. This is simply another way of writing the same vector of vector u. So sometimes this is referred to as ij form for vectors, or unit vector form. So we'll refer to that as unit vector form. So notice when I use unit vector form, I don't say 3i, 2j. That doesn't make sense. That's a big no. We also would not say 3i plus 2j and put that in angle brackets. That's a big no as well. So notice that it's one or the other. You either describe the terminal point of the vector in angle brackets, or you represent the vector as a sum of horizontal and vertical unit vectors. Now, one more aspect of vectors that we're going to be able to find is the angle between two vectors. So let's assume that we're given vectors u and v, and let's just say that we'll say that u is the vector, just to make it consistent so we can see what it is. It's u1, u2. Okay, and let's say that v, the terminal point of v, is going to be v1, v2 in angle brackets, our component form. Now, in order to find the angle between two vectors here, the way that we're going to do this is by using the law of cosines by being given u, w, and v. So think about what w is. If I were to look at these two vectors, u and v, then I could see that in order to get w, I would simply add v plus w. Remember that that's saying that v plus w, adding w onto the end of v, is equal to u. So in other words, we now know that w is the vector u minus v. Okay, so now we see that w has the component form by just subtracting the two quantities of u1 minus v1 and u2 minus v2. So now, based on our law of cosines, I should be able to recognize that the angle theta is opposite the side length of the magnitude of w. So since theta is opposite w, my law of cosines is going to start with the magnitude of w squared is equal to the magnitude of u squared minus the magnitude of v squared, or plus rather, I'm sorry, minus 2 times the product of these two, so the magnitude of u times the magnitude of v, times cosine of the angle between them. Now notice the angle is what I'm trying to find. I'm trying to find what theta is. And so we're just going to go ahead and start to determine what each of these quantities are by rewriting the magnitude of w squared. So notice that that piece is simply going to be the square root of u1 minus v1 squared plus u2 minus v2 squared. And if I replace the magnitude of u over here, that gives me the magnitude of u squared, which is u1, I'm sorry, this should be squared. Okay, and then I've got u1 squared plus u2 squared. But notice that I'm also squaring that quantity. And then I use the magnitude formula for v, which is the square root of v1 squared plus v2 squared. But I'm supposed to find the magnitude squared, so I'm squaring that as well. Minus, and I'm just going to keep these magnitudes as is for now. So I'm going to say the magnitude of u times the magnitude of v times cosine of the angle between them. So notice what's helpful about this is that squaring the square roots cancels all the square roots. So I'm just going to expand this quantity to get u1 squared minus 2u1 v1 plus v1 squared. And then we'll expand this quantity, which gives me plus u2 squared minus 2u2 v2 plus v2 squared. And notice that on the other side, if I square each of those square roots, those quantities just cancel. So we're left with u1 squared plus u2 squared plus v1 squared plus v2 squared. And we're still left with this minus 2 times the magnitude of u times the magnitude of v times cosine of theta. But what you should recognize here is that if I subtract u1 squared from the right side, it'll cancel on the left. And the same thing with u2 squared, it'll cancel from the left. Same thing with v1 squared, it cancels from the left. And the same thing with v2 squared, it cancels from the left. So all we're left with here is negative 2 u1 v1 minus 2 u2 v2 is equal to negative 2 times the magnitude of u times the magnitude of v times cosine of the angle between them. But notice how every term has a coefficient of negative 2. So I can cancel that quantity by dividing, giving me u1 v1 plus u2 v2 is equal to the magnitude of u times the magnitude of v times cosine of theta. So that's what happened when I divided by negative 2. Now, if I want to find theta, then all I'm doing at this point is dividing by what's in front of cosine theta. So that means that I have a formula that says cosine of theta is equal to u1 v1 plus u2 v2 divided by the magnitude of u times the magnitude of v. And that is the formula for how we're going to find cosine of theta. So if we now are given, going back to the beginning here, if we're given vector u, which is a x and y coordinate, and we're given v, which is also an x and y coordinate, then all we need to do to find the value of cosine theta is to simply take the product of the two x coordinates, the product of the two y coordinates, then add them together. And what that gave me is something very important in physics applications referred to as the dot product. So when we take a look at the dot product of u and v, the dot product is, first of all, referred to by the notation u dot v. Now, it's important not to say times, because there is no real multiplication of vectors. I can multiply a vector by a scalar, but I can't multiply two vectors together. But what we should recognize here is that this u1 v1 plus u2 v2 is the formula for the dot product. Let's take a look at what that means. When I say u1 v1, that's just simply saying multiply the x component here times the x component here. Then it says multiply the y component times the y component, then add them together. And that's exactly what u dot v is going to be. So we simply have u dot v is equal to the product of the x coordinates plus the product of the y coordinates. Which means that we can actually rewrite that numerator as u dot v. And we're dividing it by the product of the magnitudes. Now we can say here times the magnitude of v, because notice that these two quantities are magnitudes and I'm able to multiply real numbers. So in the bottom, this is in fact multiplication. Okay. So notice that this, in fact, in the denominator is multiplication, while the dot in the numerator, because it occurs between two vectors, is considered a dot product. And therefore, we've got a formula that says to find the angle between vectors, we're going to say that theta is equal to cosine inverse of the dot product of the two vectors divided by the product of their magnitudes. So although this formula for finding the angle is a bit more complicated than adding and subtracting vectors, it's only using the two vectors u and v in order to find that angle. So let's take a look at an example. Now there are some very interesting facts that we can tell about the angle between vectors when we take a look at the fact that cosine of theta is the dot product over the product of the magnitudes. Now the reason why this is such an interesting relationship is because sometimes we realize that cosine of theta is positive, negative, or zero at different times. Now cosine of theta is going to be greater than zero when theta is in the first quadrant. So when theta is in quadrant 1, right? So that implies that when cosine theta is greater than 0, then that means that theta is an acute angle. But I'd also like to help you recognize that the magnitude of u and the magnitude of v are lengths. So since those are lengths of vectors, they're always positive. So the only thing we really have to take a look at is the dot product. So what that also implies is that theta is acute when the dot product is positive. So the dot product actually alone tells us something interesting about the angle between vectors. We can also take a look at when cosine of theta is less than 0. Now, if you think when cosine theta is less than 0, well, that's going to happen, obviously. Now, when we're talking about angles between vectors, they always have to be somewhere between 0 and 180. Because if I have something like this, two vectors, I would never say that this is the angle between them. The angle between them is actually going to be the angle that's between 0 and 180. That's the angle we're referring to. So we know that when theta is acute, then that means that the angle is between 0 and 90 degrees, so the dot product would have to be positive. But I know that cosine of theta is less than 0 in the second and third quadrants, but the angle between vectors could never be a third quadrant angle, so that's only going to happen when theta is in quadrant 2. Now, if theta is in quadrant 2, that means that theta is an obtuse angle. It's between 90 and 180. But again, thinking about that, again, if we know that cosine of theta is going to be negative, that means this whole quantity here will be negative. But we also know that the magnitudes are always positive. So the only way for this quantity to ever be negative is if the numerator is negative. So in other words, I know that when the dot product is negative, then the angle between them will be obtuse. So again, just by calculating this very simple dot product, we're going to be able to already understand whether or not the angle between the vectors is obtuse or acute. But there's one more possibility here. The last possibility is that cosine of theta could be equal to 0. And cosine of theta is equal to 0 when the angle equals 90 degrees. So that would imply that the vectors, so the vectors are perpendicular to each other. So if the angle between them is 90 degrees, then the vectors are perpendicular. But we give that another name. When two vectors are perpendicular, we say they are orthogonal. Let's go down here and say that is orthogonal. So two vectors are orthogonal when the angle between them is 90 degrees. But again, if we go back to our formula here, the only way for this for the cosine value to be 0 is when the numerator is 0, right? So that's going to happen when theta is 90 degrees, and therefore, when the dot product is equal to 0. So this is a very helpful tool for being able to determine whether or not the angle between vectors is either positive, negative, or 0. And if the dot product is equal to 0, then that automatically tells us, without doing any more work, that the two vectors must be orthogonal. For our last example, we're going to go ahead and try to find the angle between these two vectors. Now I'm curious as to whether or not these are orthogonal. So the first thing I'm going to do is I'm just going to take the dot product between the two vectors and determine if the answer is 0. So I know the dot product is negative 2 times 5 plus 3 times 1. And notice the way that we did that is we multiplied the x coordinates of negative 2 and 5. Then we multiplied the y coordinates of 3 and 1. And then we added the results together. So that gives me negative 10 plus 3, which is negative 7. So because u dot v is negative 7, that tells me a few things. It tells me that these vectors are not orthogonal, which means that they are not going to form a 90-degree angle. It also tells me that because the dot product is negative, that means that this numerator will be negative. And because the numerator is negative, cosine is negative and therefore obtuse. So I already know, based on the fact that the dot product is negative, that the angle will be obtuse. So while we're at it, we need to make sure that we're finding our magnitudes of each of these quantities. So let's find our magnitude of u. Now remember, the magnitude of u is nothing more than the square root of negative 2 squared plus 3 squared. So 4 plus 9 is 13, and therefore we're left with the square root of 13, which is of course positive because it's a magnitude, it's a length. If we now take the magnitude of v, then that's the square root of 5 squared plus 1 squared, which is the square root of 26. So now if we just plug in each of those quantities, we know the cosine of theta is equal to the dot product of negative 7 divided by the square root of 13 times the square root of 26. Now we can maybe simplify that a little bit if we choose to. You could see that the square root of 26 is the square root of 2 times 13. Which normally wouldn't be that big of a deal, but the fact that it's 2 times 13 means that I'm multiplying root 13 times another 2 times root 13, which means that this can actually simplify to become cosine theta equals negative 7 over 13 times the square root of 2. But now we have to take the cosine inverse of that function and realize that if I take negative 7 and divide it by 13 times, actually we should put this here, let's start that over. So negative 7 times the quantity, so in parentheses, 13 times the square root of 2. I keep making a mistake. Negative 7 divided by the quantity of 13 times the square root of 2. And we want to make sure that we're punching it in correctly, so we could see negative 7 divided by 13 times the square root of 2. And there's our answer. Now, notice how cosine of theta is this negative quantity. We now need to take cosine inverse of that and realize that my angle is approximately 112.38 degrees. So coming back here, we know that theta is equal to cosine inverse of -7/13√2, which is approximately 112 degrees. And that's the angle between the two vectors. So today we've learned all kinds of different processes of being able to do operations with vectors, being able to add them, subtract them, take scalar multiples of vectors and determine what those look like on a graph, finding dot products and angles between vectors. So there's all kinds of things that we can now do with vectors in order to help us with the applications that we're going to be faced involving trigonometry and physics.